So the first thing we're going to do is draw our little scenario up here. So I have the wire at a length of L, and the location is on the Y plane. So our entire system here is on the XY plane. That tells me that the magnetic field is going to be of the Z components, negative or positive. And with the right hand rule, um, I can tell right off the bat that it's going to be into the paper. So it's negative. What I have right here, um, delta B is into the board, the magnetic field. So I'm started with the basic formula right here for the magnetic field. I kind of wanted to start right at the beginning so I can tell like exactly where everything came from, and it was kind of confusing, but I think I pretty much figured everything out. I think a lot of stuff in this formula is pretty unnecessary, but it better explains exactly why you do what you do in this formula. So I go from this step to this step. I pretty much just added in the magnitude of r here. So it was r squared. If you fill in the square root of x squared plus y squared, it just ends up being x squared plus y squared. No square, no square root, nothing. So then from there, we can rewrite delta L. Um, it'll be the change in the length of this. So we're pretty much evaluating it from um, a large number of separate pieces further and further and further out with respect to this point here. So we can rewrite the change in L as I delta x, because our x is changing, and then times the vector of x. I think that that's pretty. Um, I don't know if that step was really necessary, but as far as showing where it came from, like I said, and then times the r hat from up here, just brought it out there. So the next couple steps, I'm just going to pretty much be figuring out what is r hat. So the vector r is going to be x, y, 0, because of course it's on the xy plane. The z component is going to be 0, and it's going positive x and positive y. And then the magnitude again is this distance from our observation point to our delta x, well, wherever the change in L is. So we got the square root of x squared plus y squared. So then r hat is going to be the r vector over the magnitude. So in this next step, I'm pretty much just filling in r hat up here for the cross product. And when you cross the top, these two vectors here, you're going to end up with 0, 0, and y, which, let's see. Okay, yeah, and then when you cross product these two scalars, I guess you can say it's just the same as multiplying them together. So when I bring my y into this formula, let's see, it pretty much changes the top into I, y, delta x, and then the bottom is going to be x squared plus y squared raised to the 3 over 2, which the 3 over 2 just comes from multiplying these two denominators together. And then I set up my integral. It's going to be from negative L over 2 to L over 2. So from the left side of the wire to all the way to the right side, I'm integrating the whole thing. And it always is easier for me to rewrite these fractions as, if it's 1 over something, I just rewrite it. So that's what I did over here, is just to make it easier to integrate, which I didn't even do. But again, I think it's something that's integratable if I rewrite it like this and use like the product rule. So that's about it.